Hmm. Okay, I have shared my screen. Yeah, is it visible? The screen is visible to all.
Yes, sir. Yes, sir. Sir,
Okay.
your voice is a bit low. It's not audible properly.
Okay, let me increase the volume. Okay, I have increased the volume of my laptop also. Is it now okay? The voice?
Yes, sir.
Okay. Okay. I'm also hearing louder your voice. Okay, fine. So this is good. So what will I do is uh, okay, look at this picture that I have shared. Look at this picture. This picture is figure 3.1 from Wallstead. Okay, figure 3.1. The first transistor, courtesy Bell Telephone Laboratories. So this was the original transistor that was actually fabricated by those three persons, okay, and who later got Nobel Prize for this also. So this was the first working transistor. Okay, it may not be visible, it may not be clear that how where are the terminals and those things, but if we can pay a little bit of attention, okay, this might be the one of the terminals. This might be uh, one of the terminals, and this might be the third terminal. I'm also guessing, but I hope that these are the three terminals, and this is the body. Okay, this is the body, and and these are the terminals taken out from here. Okay, so some portion might be emitter, some might be base, some might be collector, like that. Okay, okay. So if I constructions we had seen a little bit. Let me go through it again. So we have three terminals. We have three terminals: emitter, collector, and base. Okay, and this is a bipolar device. The transistor is a bipolar device. Okay, the name consists bipolar junction transistor. So what is the meaning of this term bipolar? Okay, the term bipolar here reflects the fact that holes and electrons, this is important, that holes and electrons both participate in the injection process into the oppositely polarized material. Okay, so this in simple terms, I can tell that the bipolar device means both type of charge carriers will participate in the conduction of current. Okay, that both holes and free electrons uh, participate in current conduction. Okay, just a minute. My daughter. Okay, she slept again. Fine. So this is important here that BJT is a bipolar device, means that both type of charge carriers, that is holes and electrons, will participate in the current flow that occurs through the device. Okay, and in contrast to this, uh, yesterday I told about another device, that is field effect transistor, and we will see later on that field effect transistor would be a unipolar device, not a bipolar device. So it means that either of these two charge carriers, either holes or free electrons, will will help in the conduction of current through the device. Okay, either holes will be there or electrons will be there. You will not find both type of charge carriers flowing inside a FET device. Okay, so this is one of the most basic difference between FET and BJT. Okay. uh, okay. Now next we will see about the operation of transistor. Okay, that how does the transistor operate? Basically, it means that what are the different currents that flow inside BJT, inside this device. Okay, we will see about it. Okay. And before going through this, just try to recall that how was the current conducting inside diode. You can just try to recall that. Okay, so uh, in if you recall that for the case of our diode, you had we had one forward bias case and we had the other case as reverse biased. Okay, and can you remember that what was the amount of current, or how does the current uh, flow when it is forward biased, and what type of current flows when it is reverse biased? Okay, in forward bias the amount of current, the current is very high. Okay, and in reverse bias the current value is actually very low. Okay, this is in the range of microamperes or nanoamperes. Okay, depending on the type of material used. Okay, and what about the type of charge carriers that are involved when the diode is forward biased, or when it is reverse biased? Okay, let's try to recall this thing. Okay, uh, and here, so let us go through this step by step. Okay, go through this step by step. I am enlarging this image from Ballstead. I am again referring to Ballstead. This is figure number 3.3. Okay, figure number 3.3. Forward bias junction of a PNP transistor. If you can pay attention here, this is a PNP transistor. Okay, this is a PNP transistor. So this is uh, P type. This is N type region in between, and this is again P type region. Okay, now when we talk about one junction, let's say okay, this is the emitter, okay, this is the base terminal, and this is the collector terminal. Okay, So let us, for this time, we forget about the collector region. Okay, let us focus on the first junction, that is the junction between emitter and base. Okay, and we call this as the emitter base junction. Okay, so emitter base junction, or EBJ. So this is this thick, vertical thick black line is the junction between the P and the N, or between emitter and base. So this is the emitter base junction. Okay, so and I told yesterday that most of the time we will be using this BJT to design amplifiers. Okay, and for amplifiers, or for amplification purpose, if you can remember that, yeah, this is working. Okay, right, this is working. So sometime in between, I had to confirm that whether my internet is coming or what. Okay, and for amplification purpose, what should be the biasing of emitter base junction? We will use the forward active mode or the active mode. And for active mode, the emitter base junction should be forward biased. Okay, so we'll try to forward bias the emitter base junction like this. Since this is a PNP transistor, so P type region would be connected to the positive terminal of this battery. Okay, so let's say this is V something written VEE or whatever. We can give any name. Okay, so let's say this is one battery, and this is the positive terminal of the battery, and this is the negative terminal of the battery. And from making this junction as forward biased, okay, the P type would be connected to the positive terminal of the battery, and N type base region would be connected to the negative terminal of the battery, like this. Okay, and this will make this emitter base junction forward biased. Okay, now what would be the current flow in this under this biasing? Since this is a forward bias junction, this is a forward bias case of a diode. Okay, can anyone tell me that what would be the direction of current, and what charge carriers would it consist of? You can just apply the concept of forward biasing mode from the diode directly here, because diode is nothing but a PN junction, and we are referring a PN junction here. Okay, right now just forget about this portion collector, just focus on this particular region, this junction.
BJT charge carriers will flow in the circuit.
Which charge carriers? Majority charge carriers will flow in the circuit. In which direction? In what direction? Left to right or right to left?
They're
Okay,
from
left to
left to
right.
right.
Okay, and okay, right. Why would it be like this? Because look at here. This is the positive terminal of the battery. Okay, and this is p-type material. So p-type material is having very large number of holes as compared to electrons. Okay, positively charged holes would be in large number in p-type as compared to electrons here. Okay, and this is the positive terminal of battery. So this positive polarity of the battery will repel the positively charged holes from this p-type material, p-type emitter, towards the n-type base. So here I can write that holes will travel to right in this direction. Okay, and electrons which are very few in number, okay, which are very few in number, okay, will travel in this direction. Right, as far as this emitter region is considered. Okay, let's go into the base region. Okay, the base region is thin as compared to the rest of the emitter region. Okay, again, and here the base region is n-type material. Okay, n-type material, and is very light doped as compared to emitter doping. Okay, remember this fact. Emitter is very thick and heavily doped, as compared to base. Okay, and base is very thin and very light doped as compared to emitter. Okay, so if the base is very thin and the doping level is very light, the doping level is very low as compared to emitting at
Excuse
the
me,
number
sir.
of charge region.
Sir, sir, your voice is not audible clearly. Sir, and your screen is also not visible.
Okay, students, is it clear? Hello, students.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, 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 fine. So overall, the current direction would be from left to right. That will be in the direction of the flow of holes and will be in the direction of
Excuse me,
up.
sir.
Yeah. Hmm.
So your screen is not visible, sir.
Okay. Okay. Now I have shared it again. Yeah. Visible now?
No, sir, it's not visible.
Okay, but I have shared. Some of you might be able to see.
Sir, the screen is there, but I mean the contents of the screen are not visible. Only M is showing, sir.
Content is not showing. Okay. Okay. This figure is visible.
No, sir.
No.
No, sir.
No, sir.
Okay. Okay. So.
Yes, sir. Now it's
Yes, sir, now it's visible.
Okay. Chalo. I will draw the figure here. Okay. We take suppose here. Let's assume this is P, this is N, this is P. Okay. So since this is PNP transistor, okay, this is emitter terminal, this is base, and this is collector. So we have two junctions. We have the emitter base junction here, and we have the collector base junction here. Okay. So I will focus one by one. I'll focus first on this emitter base junction. Okay. We know that this emitter is p-type material, so it will contain more number of holes which are positively charged, okay, as compared to the number of free electrons which are negatively charged. Okay, the number of holes would be very high. Number of holes would be very high as compared to the number of free electrons, because this is p-type material. Okay, at the same time, since the base is n-type, okay, and also remember that the base is very lightly doped as compared to emitter, so it will contain more number of electrons as compared to the number of holes. Okay, because this is n-type. Okay. Okay, but the number of electrons here would be very less again as compared to the total number of holes, because the thickness of emitter is more, first thing, and also the doping level of emitter is high, very high as compared to the doping level of base. Okay. Now let me bias this. So I will forward bias this because I want to use this for amplifier for amplification purpose, and for amplification purpose I need to forward bias the first junction, that is emitter base junction. Okay. So let's say this is any battery that I have connected here. The p-type material is connected to the positive polarity of the battery, and the n-type base is connected to the negative polarity of the battery. Okay. This positive polarity of the battery will repel holes, okay, holes in this direction, the holes will move in this direction from left to right. Okay, holes will move in this direction. Okay, and at the same time, the positive polarity of the battery will also attract the negatively charged free electrons from this emitter region. So electrons will move from right to left. Okay, and this will be the case for base also. This will be the case for base also, and we know that since this is forward biased, so as a result of this, the thickness of the depletion region at this PN junction would be very less, would be negligible. And in the case of forward bias, the amount of current that flows through it is large. Okay, so if holes are traveling in this direction and electrons are traveling in this direction, so because of these two, the overall current that will flow in the direction of holes and in the opposite direction of electrons, so we can say that the current that will flow through this junction would be in the direction from left to right. Okay, so I can write the current direction would be like this, that is in a clockwise fashion. Okay, so it will be traveling from left to right as far as this junction is considered, and as far as this whole loop is considered, the direction of flow will be in clockwise. Okay, right? Is it clear?
Yes, sir.
Okay, fine. Now, uh, this we here we have taken into account the first emitter base junction. Okay, now let me quickly draw the case for the next junction, that is the collector base junction. Okay, so taking the same PNP transistor, okay, this is P, this is N, this is again P. This time we'll take the case for this collector and base junction. Okay, so we'll not bother about emitter base junction because we have already seen that. Okay, now for collector, we know that for using this as an amplifier, the collector base junction should be reverse biased. Okay, and the collector is P type, so again it will contain more number of positively charged holes. Okay, as compared to few negatively charged electrons. Okay, and the base is n type, so it will contain more number of free electrons. Okay, as compared to the positively charged holes. Okay, but overall, because the thickness of collector is again the thickness is more as compared to the thickness of base. Okay, and also the doping concentration, the doping level of collector is very high as compared to the doping level of base. So overall the number of holes would be very large as compared to the total number of free electrons. Okay, the same case will exist here also. Now let me make it reverse bias. Okay, so P type should be connected to negative terminal of the battery, and N type should be connected to the positive terminal of the battery. Okay, and any battery. So this will make this junction the collector base junction, in the reverse biased mode. Okay, and what happens in the case of reverse biased mode? We know that in the case of reverse biased mode, the depletion region, what happens to the depletion region? Does it reduces or does it become more wide? It become more and more.
What?
Wide.
Yeah, it becomes more wide, that it becomes wider. So I can show it like this, that it will grow wider, and it will like grow like this in the collector region. It will also exist in the base region also, like this. Okay, so this will be the case for, this will be the region for depletion. Okay, and the depletion region stops the flow of current through the junction. Okay, so what happened, the majority charge carriers will not flow across this junction, but we know that in the case of reverse biasing, there still exists a very low amount of current. Okay, and that is because of minority charge carriers. So the current will flow because of minority carriers. Okay, and the direction of the current in this case, the direction of the current in this case would be like this, from left to right. Okay, and it will be in the direction like this, clockwise. Minority charge carriers, which are the minority charge carriers? The minority charge carrier, can you tell me? Okay, I have told about that minority charge carrier will flow in this direction, fine. Okay, but for collector, the minority charge carrier is electron, and for the base, the minority charge carriers are holes. Okay, so there are different minority charge carriers for base and holes. So can you tell me overall what are the minority charge carriers, whether electrons or holes, that will consist this current, that will make this current? Yeah,
Electrons. Electrons.
electrons. Hmm. Okay, and what about holes, which are minority charge carriers in base?
Holes.
Holes. So holes or electrons or both?
Sir, electrons.
Electrons are the minority charge carriers for p-type material, p-type collector, right?
Yes. Yes,
But
sir.
what will happen to the minority charge carriers of base, which are nothing but holes?
Sir, they will
What will happen?
neutralize.
They will neutralize. So, and why would these minority carriers will not neutralize? So my question is, the what type of minority charge carriers? Because the minority carriers are different in the case of p-type and in the case of n-type material. Okay, so if I'm saying that these are minority carriers which are constituting the current flow in this fashion, so I'm telling that, I could say that the minority charge carriers of B as well as the minority charge carriers of N. Okay, so what happens actually? I will try to explain very shortly that. Look, when the thickness of this depletion region increases, okay, okay, and we have applied an external battery B. Okay, so because of this externally applied battery, okay, the thickness increases, right? But at the same time, there exists an internal electric field within this depletion region. Okay, within this depletion region, there exists internally electric field. Okay, and the direction of electric field is such that, okay, it will help the holes from base to be swept away in the collector region, and it will also at the same time help the minority charge carriers, that is electrons from the collector, to jump into the base region. So both type of charge carriers are actually involved, but since they are minority charge carriers in their case, okay, they are present in very low quantity in the respective regions. So overall, the amount of current that flows, the magnitude of this current is very less. Oh, okay, they are in the region of nanoamperes or microamperes, depending on the type of material used. Okay, so what happens is that I can draw a total complete scenario like this. Okay, so if I'm having a PNP BJT, uh, PNP BJT. This is P, this is N, this is P, this is emitter, this is base, this is collector. Okay, so let me make this forward bias like this. Okay, and this collector base junction should be reverse biased. I will combine these two cases now. Okay, I will combine these two cases. So in the first case, we had seen that when this emitter base junction was considered, we had majority charge carriers that were flowing from left to right. So I can, and since the number of charge carriers were large, so I can represent them with the help of a thick arrow like this, a thick arrow like this. Okay. The thickness means the amount of or the number of charge carriers are large. Okay, fine. And when we talked about base junction, we saw that there existed a very small amount of current, and that was because of minority charge carriers. So, and the direction was again left right. So I will represent this by a thin arrow flowing from left towards right. Okay, and let's say I can represent like this. This is the depletion region. This is depletion region. Let's say. Okay. Okay, fine. And this is the depletion region for emitter base junction, which is very thin. Although I'm not drawing here, but you assume that this is thin, very thin as compared to the depletion region for collector base junction. Okay, so uh, this is because of majority charge carriers, and this is because of minority charge carriers. But the direction of flow of current is same for these two cases. Okay, now there's one more thing that is to be added here, that this is because of majority charge carriers, which are holes in the case of this emitter. Okay, so actually holes are flowing from emitter to base. Okay, emitter to base, holes are flowing, right? And they are when the positively charged holes are entering into the base region here, which are still positively charged here. Okay, now because of the existence of this depletion region, which contains very strong electric fluid. Okay, and because of the existence of this battery, external battery. Okay, so whatever holes enter from emitter to base, okay, those are instantly swept away by the collector region, because this is negatively charged negative polarity of the battery. So they will attract the positively charged holes which are coming from emitter into base. Okay, so these positively charged holes will be swept away, uh, will be uh, will be attracted by the negative polarity of this battery whenever they enter into the base region. So from emitter they enter into the base, and then from base they enter into the collector immediately. Okay, and they will flow like this. They will continue to flow like this. Okay, this is one thing. And this we are already clear that this is because of the minority charge carriers. Okay, now, but there is one more point that has to be included here, that uh, holes are entering from emitter to base. Remember, holes are entering from emitter to base. The base is of opposite polarity, opposite nature. This is n type, the emitter was p type. Okay, and in base the number of free electrons are more, although the total number of free electrons will still be less as compared to the number of holes that are entering here. But still, if you talk about the base region in its entirety, the base region contain more number of electrons as compared to holes. Okay, so when holes are entering from emitter to base, which contain more number of electrons, so there is a chance that some of those holes which are entering into the base region may get neutralized by the negatively charged electrons which are already present in the base region. Okay, we know that whenever a hole combines with a free electron or simply a moving electron, what is the result? What is the process? This process is called recombination, and the result of this process is a valence electron. Okay, and this valence electron is not capable of moving. This will not move. This cannot move. This can't move. So earlier we had a hole and free electron, both were contributing in the flow of electric current. But when they combine, when they recombine, they turn into a valence electron which is not capable of moving, and hence which does not contribute in the flow of electric current. So we have lost some amount of electric current because of this recombination process. Okay, so when holes enter into the base region, small portion of those will recombine and they will turn into valence electron. Okay, and I will show this by a very thin arrow signifying that the rate of recombination that is occurring here is still small as compared to the thickness of uh, this arrow. Okay, okay, but again, whatever things are lost here, that has to be supplied by these two batteries. Okay, and that will result in a small amount of current flow through the base region.
Excuse me, sir.
Yeah,
Sir,
Sir,
we have chemistry
we
class
have to
at 4.
yeah, I know that you have chemistry class. So I have 5 minutes left now. I will complete this. Okay. So overall,
Okay, sir.
the emitter current would be in this direction, IE. Okay, and the base current would be in this direction, that is IB. Okay, and the collector current would be in this direction. Okay, so the direction of currents is such that is the value of collector current is equal to the sum of the base current and collector current. Okay, right? And uh, we can see that the collector current consists of two arrows, one thin arrow and one thick arrow. The thick arrow is because of the majority charge carriers, and the thin arrow is because of the minority charge carriers. Okay, so we can write that IE, okay, that is IC, that is the collector current, consists of the IC majority, okay, plus ICO minority. So collector current consists of two components: one majority current, majority charge carriers part, and the other minority charge carriers part. Okay. And if I want to talk about the units, the value of IE and IC would be almost same, and that will be in the range of milliamperes. Okay, and the value of IB, that is base current, would be very low, and they will be in the range of microamperes. Okay. Okay. So remember that the value of base current is very less as compared to the value of collector current or the emitter current. Okay, this is what uh, I am trying to say. So these things are important. These four equations, these two equations, and these two things. Okay. So tell me if this is clear up to this portion. So tomorrow we will start from here. We will start the next topic, that is about transistor, different transistor configurations, characteristics. Yeah, students, is it clear, or is there any doubt?
Yes, sir, clear.
Okay. I think the strength of mass is 55, right?
65, sir.
So why the, okay, 65, fine. But why then the number of participants are less, only 39? Out of these, two are mine too. So only 37 students are present here. So you inform other students accordingly. They should join the class. Okay. Otherwise, it will affect their attendance percentage, which may cause in future problems. So avoid that thing. Okay. Do one thing. Give your attendance in the chat box. Write your roll number and name. I will take this. I will note those things for the attendance. Give your roll number and name, and then you can leave. Or if someone is having any doubt, he or she can ask.
Excuse me, sir.
Yes.
Could you please explain FET once more?
FET.
Yes.
FET, we will come. It is there in the next module. Okay, we will come to this. We will come to the portion of FET in detail. But just for quick knowledge, I can tell that the FET stands for field effect transistor. Okay, and it's a unipolar device. It is a unipolar device, which means that either electron or hole. Okay, either electrons or hole will consist of electric, which will consist of electric current. Okay, either electron or hole, not both, because it's a unipolar device. And why is it so? What are the different what is its structure, and how is it conducting? We will come to the behavior, we will come to the working and circuits, all these things in the next module. But just for the comparison purpose between FET and BJT, just you can remember these points. Okay.
Yes. Yes.
Okay, anyone else? All of you, please give your attendance in the chat box. Write your roll number and name. And then you can leave. So I will stop sharing now. Stop recording.